Clustering. In the parametric approach, we assume that the sample comes from a known distribution. In cases when such an assumption is untenable, we relax this assumption and use a semi-parametric approach that allows a mixture of distributions to be used for estimating the input sample. Clustering methods allow learning the mixture parameters from data. In addition to probabilistic modeling, we discuss vector quantization and hierarchical clustering. Introduction. In chapters 4 and 5, we discussed the parametric method for density estimation where we assumed that the sample X is drawn from some parametric family, for example Gaussian. In a parametric classification, this corresponds to assuming a certain density for the class densities P of X conditioning on C1. The advantage of any parametric approach is that given a model, the problem reduces to the estimation of a small number of parameters, which, in the case of density estimation, are the sufficient statistics of the density. For example, the mean and covariance in the case of Gaussian densities. Though parametric approaches are used quite frequently, assuming a rigid parametric model may be a source of bias in many applications where this assumption does not hold. We thus need more flexible models. In particular, assuming Gaussian density corresponds to assuming that the sample, for example, instances of a class, forms one single group in the d-dimensional space, and as we saw in chapter 5, the center and the shape of this group is given by the mean and the covariance respectively. In many applications, however, the sample is not one group. There may be several groups. Consider the case of optimal character recognition. There are two ways of writing the digit 7. The American writing is 7, whereas the European writing style has a horizontal bar in the middle to tell it apart from the European one, which keeps the small stroke on top in handwriting. In such a case, when the sample contains examples from both continents, the class for the digit 7 should be represented as the disjunction of two groups. If each of these groups can be represented by a Gaussian, the class can be represented by a mixture of two Gaussians, one for each writing style. A similar example is in a speech recognition where the same word can be altered in different ways due to different pronunciation, accent, gender, age, and so forth. Thus, when there is not a single universal prototype, all these different ways should be represented in the density to be statistically correct. We call this approach semi-parametric density estimation, as we still assume a parametric model for each group in the sample. We discuss the non-parametric approach in chapter 8, which is used when there is no structures to the data and even a mixture model is not applicable. In this chapter, we focus on density estimation and defer supervised learning to chapter 12.